Good morning, good afternoon, or good evening, wherever in the world you are. Now, the advent of the internet has made connectivity to internet resources almost mandatory. Certainly, with a lot of people working from home, it has become an imperative. Not only has it become an imperative, but also high-speed internet is required, for instance, for video conferencing or webinars as this one. Now, the ultimate in connectivity is still optic fiber for the large bandwidth achievable using this medium, but it is often very impractical and more expensive due to the necessity to install fiber optic cables. So this is where radio or wireless transmission of data really shines, particularly due to the modern advances in creating fast, reliable wireless transmission that is relatively inexpensive compared to optic fiber. However, the installation of radio and where it is located in a building or in a home is key to take advantage of these modern high-speed wireless techniques. Now, I say where it's located because being wireless or radio transmission, the reliable reception of the radio signal is key to the success of this medium. And the advantage brought at least by technologies such as LTE or long-term evolution as it's called, and we're going to talk about 4G, 5G as well as far as the antennas are concerned. So this is where a good antenna installation becomes extremely important, and in the following presentation I'm going to tell you the why, the what and the how. Now my presentation will be very informal, in the sense that I've invited, as Ilana has mentioned, a panel of my colleagues to jump in during the presentation. I know that they are eager to answer some questions during the Q&A session as well. Right, so let's look at the agenda. First of all, I'm going to talk about what is an antenna, and I'm going to look at the fundamentals of antennas. So the webinar is really aimed at understanding what antennas are all about and how they help you in receiving a good LTE, a 4G or a 5G signal. So how does that external antenna improve your LTE performance? I'll show you exactly how that antenna assists you in gaining a good signal. So we're then going to look at the general concepts when selecting an LTE antenna. Afterwards, we'll have a look at choosing the correct antenna. It's important to understand which one is the correct one after we've understood the general concepts. And then last and certainly not least, I'm going to show you what this increase means in practice. Now, as a footnote, as part of the presentation, we're going to give you a list of cheat sheets that and links to our website. Right, so let's first look what is an antenna. I'm going to show you a little practical demonstration. I've shot a video in my RF lab, and that is going to consist of a transmitting antenna with a little oscillator that creates an electromagnetic wave. We'll have a receiving antenna. That receiving antenna is going to, as we switch on the oscillator, is going to get an electromagnetic field induced in it, and you'll see that little LED that shows us the current that's being induced lighting up. Now, let me just say for the purists, the electromagnetic wave is slightly different from what this is. This is the near field. This is magnetic induction, but the principles are very much the same. And in a demonstration like this, you will see how, for instance, if we move the antenna away, the LED which shows the current that's being induced will switch off, so to speak, showing that no induction is happening. So without further ado, this is my little RF lab, and I'm going to play a video for you, and I'll summarize afterwards. Is the sound coming up, Ilana?
Nope, not at the moment. Let's just give it a minute. Not hearing anything yet, Peter.
Let's see what's happening there. Yeah, my apologies, guys. This was working, so it's.
There's the play. That's it, because it's such a nice video.
Is the sound coming through?
Nope, not hearing sound, but maybe you can explain while you're
Okay,
busy.
well, let's do that. I'll just explain as it goes along. It seems that we've got the sound's not coming through there. Okay, not serious. I'll play the video. As the video plays, I'll explain to you what's happening there. So what I'm going to point at over there now is, let's just get it to play. So that is like I've shown previously, that is 50 turns of enameled copper wire. That's going to be the electrical component of our transmitting antenna. Then on this, that is going to create the electromagnetic field that our receiving antenna is going to get. That is the little oscillator that creates an alternating current. And then in the back there I've got another 50 turns of enameled copper wire. And you'll see there's an LED attached to it, which means when the current gets induced, that little LED will light up. Now, that is the oscilloscope probes. Now, oscilloscope is a device that shows the electromagnetic wave, so we can see it on the screen over there on the computer. And that means we can see what that looks like. So if I switch on, you'll see on the oscilloscope there, that's the waveform of the current that's currently oscillating in the transmitting antenna. So if I now bring the receiving antenna close to the transmitting antenna, you should see that little LED light up. Now you'll see in a moment, I've realized that the light in my little lab there is a little bit harsh, so I'm going to put a shield behind it. What I've just shown there is the inverse relationship between distance and signal. As the distance increases, the signal will decrease. As the distance decrease, the signal will increase. So there I've put a little shield so you can see the LED a little closer. There you can see the LED lighting up as the current is being induced in the LED. Right, so what I've done then is I'm just putting a little cover on there so that I can have my hands free, so I can connect the other probe of the oscilloscope, remembering that what all the oscilloscope really is a way for us to see the current. So it's in the time domain. So we look at the time domain, and we'll see the signal, and you'll now clearly see how the signal is going to be induced in the receiving antenna. There you can see the red line coming up. So I'm just, you'll see me just switching over to a slightly lesser sensitivity on the oscilloscope. Switch back. So there, that red line that you're seeing there is the current that's being induced in the receiving antenna. Right, so what I'm going to do next is I'm going to show you what happens when a router that has an inbuilt antenna is located inside a building, and you'll see me there picking up just some normal DVDs. Now, as you know, these DVDs have an aluminum surface that is the recording surface. Now that surface tends to there you can see that tends to attenuate the electromagnetic wave, or the magnetic wave in this instance, the near field. So what I'm going to do is I'm going to create a brick wall. So notice closely that I'm putting those DVDs in between the transmitting antenna and receiving antenna, and you can see on the oscilloscope how the induced signal has dropped significantly. Now, what you see me doing there is I have a metal tin top, or a tin top that's metal, and as you know, that reflects an electromagnetic or a magnetic wave in this instance. So inside a building, you will find reflections. Now watch when I create reflections. Notice that I've not put that in between the transmitting antenna and receiving antenna. I'm merely causing reflections. So what do you gain when you have an outside antenna? You gain not having reflections inside the building and not having to go through a brick wall or a concrete slab. So in summary, we have the transmitting antenna, we have the receiving antenna, we have the magnetic wave, the electromagnetic induction in the receiving antenna, and as you can clearly see from this little demonstration, having the antenna outside makes a huge difference. Okay, that's the gist of the video. My apologies for that that audio. Somehow that got lost in translation, so to speak. Okay, so let's have a look at the types of antennas. And first of all, that little whip that you have on your motor vehicle, on your automobile, like they say in the US, and that is an antenna. That's the electrical part of the antenna, very much like that loop that we've shown you. Now you may remember the television antennas. That is known as a yagi or a folded dipole, horizontally oriented or set up in this instance. Now look at the bunny ears. You may remember the bunny ears that we used to put on top of our televisions. That's just another form of a folded dipole. Then this is known as a log periodic antenna, and at Poynting we make those as well. The nice thing about log periodic antennas is that they're nice and wide band, and they have significant gain as well. And you'll see where we use them in the field. Then this is something a funny looking antenna. This is a horn antenna. I've actually designed some of these when I needed to do spectrum analysis on towers, and they typically have a fairly narrow band and a fairly high gain. Again, obviously meaning the ability of the antenna to gain a signal. Stephen, I see you wanting to jump in.
Yes. I just wanted to say that for the audience, there's a fundamental difference between your Yagi-Uda antenna, that's the TV antenna that you see on the top, and the log periodic dipole array, which is at the bottom. And the fundamental differences are that a TV antenna or Yagi antenna is very, very narrow band. And we often find people asking for Yagi antennas or LTE, and it's just not that practical because of the bandwidth of the antenna itself. So when looking for LTE 5G antenna, rather look for a log periodic dipole array, or LPDA for short.
That's it. Yes, thank you, Stephen. And so the horn antenna is a fairly narrow band antenna, and another antenna is the dish antenna. Your DSTV in this part of the world, or satellite TV, that's the antenna. So the little receiver is the little unit that sits in front. We call it an LOB, a low noise block down receiver. So something that not a lot of people are familiar with is what you see at the top there is a printed circuit board. Now, this is the type of circuit board that you find inside electronic devices, but one can very easily print an antenna. As you can see at the top of that little board there, you can see that familiar loop, which is the antenna in that particular type of antenna. Now, over here we have our cross-polarized antenna. When we say cross-polarized, there's actually two antennas inside of our Poynting XPOL. This is the XPOL 2. And when you look inside of this antenna, you'll see a really weird array of printed circuit board and reflectors, etc., which is the magic that we've designed that makes this such an excellent antenna. This antenna, incidentally, is a directional antenna. If you quickly look from the top, the car antenna is omnidirectional. We'll talk a lot about omnidirectional. The TV antenna is directional. The bunny ears is to a certain extent omnidirectional. The log periodic is directional. The horn antenna is directional, and the dish antenna is directional. But we'll cover a lot of that. Right. So let's have a look at how an external antenna improves your LTE performance. So let's look at two scenarios. We have two homesteads here. On the left-hand side, you have a homestead or a house, a building, without an external antenna, and on the right-hand side there, you can see our antenna. In this case, it's an Export 2. So let's have a look. The signal that's coming in from the outdoors is 20 dBs lower. Now, all that means is that the signal that we receive inside is 100 times smaller than the signal that's coming from outside, having to penetrate the brick wall, a slab with reinforced metal, that type of thing. So inside the building, if you look there, you can see some reflections. Now, remember that the router that's inside, or the router, as you say in America, that's inside, needs to transmit back to the tower as well. We've got upload and download. So the reflections inside actually contributes to the inability, so to speak, to penetrate the walls back to the tower. Other than that, there's noise. There's noise come from various sources, and inside a building you have a lot of other electronic devices, so that noise will contribute to interference inside, but also there's outside noise. These are things like transformers, etc., close to your home. So also any movement inside, like those reflections that we saw in our little video, can cause a problem for the signal. And what we ultimately say is that the signal that you have inside the building is between 40 and 100 times weaker, between 16 dB or 20 dBs for the guys in the know. So there we have a relatively poor signal, poor to relatively poor signal. Let's look at the outside antenna. First of all, when we put it outside, we immediately gain that between 16 and 20 dBs of better signal, so to speak. Now, the gain, although the signal outside remains the same, I've animated it there to show that the gain of the antenna is now added to the 16 to 20 dBs better signal that you have outside. Being a directional antenna, there's still noise from around the outside, but with a directional antenna, you will reduce that noise. If you look there, let me just animate it again. You see the noise signal outside being considerably less. So an outdoor antenna provides us with a very stable signal, and as the converse is true, the signal is between 40 to 100 times stronger than inside the signal, and then we add the gain of the antenna on top of it. So yes, this is where we find ourselves with a very, very good signal with an outside antenna. Right, so Stephen, you needed to say something.
Yes, Peter, just something interesting, and I don't know if you mentioned it, but this correlates quite well to your experiment. So if you look at your experiment that you did right in the beginning, showing the impact of the shielded DVD that you had, exactly the same effect happens over here. So you have a choice on the left-hand side, where you're going through the walls, going through the windows of the property. You've got reflections inside, and you have a worse RF experience. Whereas if you can capture that signal on the roof, as in the right-hand side with an external antenna, you already have a major advantage. So just a comment to relate that to your experiment. Thank you. Excellent.
Yes, thank you, Stephen. Okay, so let's have a little bit of fun here. Here we have a high-performance vehicle. Now, let's liken this to a high-performance router. Now, as you may know, part of making a high-performance vehicle really work very well is where the tire meets the tar. That's the wheels are extremely important in making this high-performance vehicle work. Now, having a high-performance router or router without a good antenna is like having a high-performance vehicle with Volkswagen wheels. You can clearly see this car is not going to perform very well with those Volkswagen wheels. Now you can go and change the car. You can go and change the router if you believe that that another router may work better. But if you keep the wheels, the wagon wheels, if you keep a relatively poor antenna, the performance is not going to improve whatsoever. A little bit of fun there. Okay. Sorry, yes, Stephen.
Peter, yes, just a comment is that we see so often that of the top quality routers, high performing routers, are often sold with out-of-the-box antennas. And so that's just something that we'd like the audience just to have a look at, is the antennas that you get out of the box are not always the same as these high-end vehicles that you have here, because they do come out with good tires out of the box, so to say.
Thank you, Stephen. Right, let's look at some general concepts when selecting your LTE antenna. Now, as you know, around you have multiple towers that are going to be providing you with a internet signal from a internet service provider. So let's look at an omnidirectional antenna. So as the name suggests, an omnidirectional antenna has the ability to receive a signal from multiple towers around it. Whereas when you look at a directional antenna, as the name suggests, a directional antenna is going to be receiving signal from a single tower. Now, there are various circumstances in which you will choose one above the other, and that's exactly what we're going to be looking at further down the line. So the directional antenna has the ability to discriminate against signals, as you can see there, that may be interfering with the signal, and that's also one of the major advantages of a directional antenna when you're having to choose to use a single tower, as you can see over there. Okay, so choosing the correct antenna, very important. So let's look at the technology, and we're going to first look at the frequency bands, how we future-proof our antennas, and we'll also discuss multiple input, multiple output, which is the acronym is MIMO. So let's look at the different frequencies that has been evolving over the years. We first had the GSM frequencies, and now Stephen may want to jump in a little bit later, because Stephen has been very involved in the world of mobile networks and cellular operators. Let me just quickly look at that. The Wi-Fi frequencies 2.4 and 5.8 was sort of developed more or less at the same time, a little bit later, but those are the frequencies used for Wi-Fi. In the US, GSM came a little later, so they were in that. You can see the frequency bands used in the US, and then later on came 3G or UTMS, Universal Mobile Telephony Services, and the 3G high-speed packet access, HSPA, etc. Then came the long-term evolution signals, and there you can see the frequencies used by long-term evolution. And then lastly, and certainly not least, are the 5G. Yes, Stephen?
Yes, just a comment over here is that as spectrum became available in these other bands and new technologies became available, the older technologies like GSM and 3G UMTS had less capacity on the networks in some cases, and some networks, some operators would actually reform that frequency band. So where you see GSM and UMTS right now could today be used as 4G or 5G frequency spectrum. So when you're looking at a 5G modem, for example, make sure that it covers all of those bands anyway, because your operator just may be using the 1800 or the 2100 band that was previously defined for GSM or 3G. So it's just something to take note of this.
Yeah, thank you, Stephen. Very, very important. And of course, equally important is the future of frequencies and how an antenna is future-proof by being able to receive all of those frequencies, and in other words, being a wideband antenna. So let's look at that. I've plotted the frequencies used by Vodacom here in South Africa, which is the local Vodafone company, and there you can see the overlay of the particular frequencies used by Vodacom. MTN in South Africa uses pretty much the same frequencies, and then if you look in South Africa, Telkom South Africa uses they use those frequencies. So just giving you an indication of how important understanding the frequency that your service provider transmits at is in terms of choosing the correct antenna. So, and there's another band that Telkom that Stephen and I discovered from frequencycheck.com. You'll see frequencycheck.com being referenced below there. Okay, so that was the looking at the technology and the frequency bands. Let's next look at the omnidirectionality that we touched on earlier. So again, like I've shown you earlier, an omnidirectional antenna is an antenna that has the ability to receive signals from a variety of towers. Now, an omnidirectional antenna allows the router or the router to roam amongst various cells. So it has the ability to get to receive multiple signals. And these days, with what is known as decorrelated carriers, we have the ability to receive a data packet, so to speak, from multiple towers at the same time. And an omnidirectional antenna is relatively easy to install because you don't necessarily have to direct it towards a particular tower. You just need to place it nice and high so that it can receive signal from all the towers around you. And then the ability of being able to get a signal from many towers around it negates the fact that it maybe have a little less gain than the other antennas, and we'll have a look at the importance of that. Now, with the directional antenna, as I mentioned earlier, this is typically where the ability to get a signal from multiple towers does not exist. You have a tower that's relatively in line of sight of you, and that's really the only tower that you can get a signal from, and that's when one selects a directional antenna. And as you can see on the graphic there, I'm receiving a signal from a particular tower, and I'm rejecting signal from other towers, simply because those signals, including noise, may be causing an interference with the signal that I want to receive. So hence the reason for a directional antenna. Yes, Stephen.
Peter, maybe jumping ahead in your discussion over here, but it's quite important. If you have a very far outlying site, if you look at the way that signal propagates over vast distances, you could have a targeted base station that would provide coverage and data throughput for your specific implementation. But other cells in distance could cause problems for you, interference. And if there's a way that you can shield yourself from those incoming signals, you actually get a better C2I, carrier interference. So we often look at vast rural sites that have very, very low signal levels to rather use directional antennas where possible. So just a comment on that.
Yes, thank you. Yes, Stephen, quite right. Thank you. So, thank you for that, Stephen. The directionality of the antenna has the effect of reducing as I've said, the interference from other directions. And so we have a high throughput on this from a single source, and one just needs to be aware that it's dependent on the cellular tower availability, seeing that it's receiving its signal from a single tower. So the next slide is one that Stephen and I discussed at length. Stephen, I don't know if there's anything in particular that you want to add to this one. What I'll do is just point out some areas of importance there. Stephen?
Yes, when looking at, for example, choosing between your LPDA and XPOL2 antenna, it's very similar antennas, but there's very minor differences. In most cases, you could actually deploy the one or the other one, and both will work just as well. So what are the fundamental differences? There are actually not many differences, except if you look at the aesthetics or visual aspects of the antennas. The log periodic dipole array is a larger, a little bit more of an uglier antenna, whereas the panel antenna can be installed and the aesthetics on the building can look better. But if you look at the reliability and the quality of the LPDA becomes better, whereas if you want MIMO, the XPOL2's already got MIMO implemented for the similar price. The LPDA, you would need 2 antennas. So why would you buy the LPDA antenna? It's purely because at the lower bands, the performance is better. At the lower frequency bands, it is much more of a rugged antenna. And so when would you choose the XPOL2 antenna? When you want simplicity, when you want something that's 95% there of the 98% there of the LPDA antenna, costs less, easier to deploy. So that really becomes the choice. It's very similar, and if you choose the one antenna over the other, it's a bit of much of a muchness in most applications. So you could actually go for either the one or the other. If you want a bit more reliability, maybe a oil and gas type of situation, I'd rather choose the LPDA. If you would rather use it in residential areas, rather use the XPOL2. But there's no hard and fast rule around this. It's just some of the options that are available with those 2 antennas. Thank you.
Thank you, Stephen. And just to point out that these are the directional antennas, as Stephen also said, as opposed to the omnidirectional antennas. There you see our OMNI 600 on the left-hand side, and the XPOL1 on the right-hand side. Aesthetic-wise, the OMNI 600 is a long antenna. It's also a MIMO antenna, and it's vertically, the twin dipoles are vertically spaced, whereas our XPOL is cross-polarized. But I'm going to explain the differences and how the use cases work in some case studies that's up ahead. So important, just a few things to notice over there. Yes, Stephen?
Yes, just over here, also just to make a comment is that, again, the 2 antennas are very similar, except that the one's got higher gain and the other one's got lower gain. So if you look at the OMNI 600, it's something that you would rather put more distant from your base stations where you have a little bit lower coverage, but it will also be suitable for dense urban areas. But it comes to its own right when you use it in residential and outer lying areas. The XPOL1, because it's cross-polarized, it will actually work better in CBD areas, built up areas where you have a lot of reflections. So that antenna will actually work much better in that environment. So that would be the decision discriminator, if you want to put it that way, is if a dense urban area, use the XPOL1. If it's a little bit more outer lying areas use the OMNI. If you wanted to use omnidirectional antennas, then that would be the discriminator between these two antennas.
Okay, thank you, Stephen. We're actually going to have a look at that in case studies to come. Just very quickly, what I'm going to discuss with you are, first of all, the routers or the routers. Here you see a number of different routers. Of course, that is the engine part of our entire operation, and our antennas obviously connect to those. Then the different connectors, there's the SMA and the reverse pin SMA connectors. We have the N-type. Typically, the N-type is used for the lower frequency bands, and we actually have antennas that we bring out with an N-type, and I'll show you one of the reasons why. And then you will find that some routers have TS9 connectors at the back. That's those little connectors on the right hand side, and we supply you with a patch lead to SMA, since our antennas come with fly leads with the SMA connectors. Then, as far as the leads are concerned, just very important to understand the importance of keeping the RF cable, in other words, the radio frequency cable from the antenna to the router, as short as possible. We typically ship our antennas with HDF 195, but here I'm going to show you that if you go beyond 10 meters, if you were to use 15 meters, for instance, rather go for a low loss cable like LMR 400 and use the N-type connectors, because as you can see on the right hand side, I'm not going to go into the whole of our cheat sheet. The cheat sheet is available, but if you look on the right hand side there, the difference between the low loss LMR and it's a slightly more difficult cable to work with, and hence the reason why we ship with HDF 195. But for the longer runs, in this case a 15-meter cable, you will get anywhere between a 2.25 to a 3.43 better performance using the lower loss cable if you had to go to a long antenna cable length. Okay, so I'm going to look at some use cases now. So here we have a summary of the antennas we're going to be looking at: the XPOL 1 5G, the OMNI 600, and I'll discuss exactly where they are used. This is the XPOL 2. The first two are omnidirectional. Now we get into the directional antennas, the XPOL 2, and the LPDA is certainly last but not least. All right, so a little bit of fun here. Here we have a scenario that we have our Poynting sales lady or our distributor or integrator sales lady asking the client how can she help, and this chap needs to know what antenna he has to use. So the first question is, where do you live and which operator do you use? So this chap lives in Calle de Castellano in Madrid, and he's using Vodafone España. So we plot the guy, and this is just a simulation. It's not an actual coverage plan. So we plot the person's home there, and then we look at the towers that surround, and there's various ways that you can find out. In this case, we've used Cell Mapper. There's various other ways to find it out. But if you plot that on a map, you'll see that these are relatively close, these different towers, and we then have a look at what the operator tells us or what Cell Mapper tells us, and the Cell Mapper tells us that those are the frequency bands. Now, the first thing then is to find out whether our antenna is going to be able to handle those bands. So again, we're looking at an omnidirectional antenna because we have these multiple towers. We want to make use of that roaming over various cells, and we are quite happy that the ease of installation is a plus, and we have many base stations that we can choose from. That's our XPOL 1. So the next thing to look at is which frequencies are used by our mobile network operator. and we plot those on our frequency spectrum map, and we see that those are the frequencies. There's another frequency there that Stephen and I picked up on frequency checker. The next thing is, however, is to see where does our XPOL one, what the frequency response is, and that is where you see the magic lies with our antennas. We cover all those bands that this chap would require to get a good signal in Madrid. Right, so we said ease of installation. We have what we call the window suckers. So if you're in a high-rise building and you need to install outside, you can even do it from the inside. You've got those suckers that'll suck onto the window pane. Stephen.
No, I just wanted to mention, but you've already mentioned it, that you can actually install this on the inside of the window. It is better on the outside, but if you're limited because your specific situation, then installing it on the inside of the window is perfectly fine as well.
Excellent. Yes, thanks, Stephen. And then you can wall mount the antenna, and you can pole mount the antenna as well. So let's look at another scenario, an urban scenario, but a low density of towers, or the towers are far apart. So we ask our normal questions, and this person stays in Sharonlea here in Johannesburg in South Africa and uses RAN Internet as a service provider. So again, we plot the towers, and in this instance, this person may have gotten the locations from the provider. We have a look at the frequencies, we plot those, and what we notice is that the towers there are multiple towers, but they are relatively far away. There's quite distances, and then we realize that we need to go for a higher gain antenna. We look at the frequencies, and our first frequency that we picked up, Stephen and I picked up more other frequencies, which I'll show you, was band 3. That's band 3 over there, and we have a look and we see that our OMNI antenna covers the band all the way from the lower 400 all the way to 3.8, and we also picked up, as I said, other frequencies, and we cover those frequencies as well. Stephen?
Peter, just to make a quick comment over here, is that as you check sites like Cell Mapper or Frequency Check, it's always good to just read up and research, because the networks might be experimenting with new frequency bands. And for that, it's good to look at an antenna that's also more future-proof, that if you do change from one network to another network, or that specific network brings out new frequency bands, then your antenna, which is already installed, is capable of those frequencies, rather than just looking at Cell Mapper and selecting only those frequency bands, which will over the longer period of time. So rather look at an antenna which is much more wideband and has performance over the whole band, would be more suitable and easier and cheaper in the long term to deploy that way.
Like a pointing antenna, Stephen. Okay, so let's look at this urban environment again. Like I mentioned earlier, we'd like to roam amongst these different towers. It is relative ease of installation. This one can either be pole mounted or wall mounted, and then the medium gain provides us with greater distance and more redundancy from the other base stations. So let's look at another scenario. And this is now the scenario where we start having to look at directional antennas. This chap has his brother living in Valencia, in a suburb, and then he finds from the network operator that the only tower that really is close by that he can use is that particular tower. He has a look and see that it handles bands 3 and band 20. And again, we do our frequency check. There are the frequency bands. We also picked up that Vodafone España uses those frequencies. And again, we do a plot and we see that our XPOL 2, which is now our directional antenna, covers all the bands that we need. extremely important to do that check. So now we're going to go to this check on the directionality. And again, let's just have a look. We now know that we, like I said earlier, that we are discriminating against signals that may impact our signal, and we're directing our antenna to the best possible tower, like our chap in Valencia. So that's the Export 2. It reduces the interference, like I've just said, and the specific base station capacity is what we're leveraging off over there, and we are dependent on that sea-level tower, but we get a very, very good signal, very, very good antenna for this particular application. So let's look at a rural scenario. So here we move to Australia, and let's say that we have a chap that lives in the outback near Perth, and his home is located there. So even though there's a tower that's close by, topographical issues is always trips us up. So there's a mountain range. And again, this is a simulation. I'm not saying that there is actually such a mountain range, but the bottom line is the installer tells this chap that that's the only tower that you unfortunately have a signal from. We know that it's quite a distance, and that's when we realize that we're going to have to go to the higher gain of a log periodic antenna. So again, we check the frequencies, and oops, we went a bit quick there. And in this instance, we see that they're also using band 3 at the lower frequencies. And remember, we said that the log periodic performs exceptionally well at lower frequencies as well. So Telstra transmits in the 1700. Stephen and I picked up some other frequencies, but again, look at the wideband capability of our log periodic antenna. Now, looking at the installation, here we have the signal being received. Now, the directional antenna has the highest gain with high directionality for those long distances from that base station. And it is a pole mount installation due to the fact that it has to be accurately, or relatively accurately at least, lined up with the base station. It is a pole mount installation. Now, we can also do a cross-polarized using 2 LPDAs so that we can get the 2x2 MIMO for enhanced performance. We literally, with the decorrelated carriers, you get double the performance using 2 antennas like you see over there. Okay, so let's have a look and see what does this increase in performance mean. And I have a little fun one again here. So here we have a scenario where on the left-hand side we have a homestead without an antenna, and on the right-hand side we have 4 homesteads, 4 houses, 4 buildings, all of these with antennas, with pointing antennas. And we're going to start a video download. Now watch closely how the video download progresses on the house, the receiver without the external antenna, and how the download proceeds on the houses with the antennas. Here we go. You'll see the started. Number 1 at the top is done. Number 2 is almost done. Without an antenna is almost halfway, and it becomes like a horse race. And number 4 is done, and now our house without the antenna is done. So in practice, that's really what we're looking at, is enhanced performance for video downloads, etc. So the built environment, let's quickly go through a selection matrix here. So as we saw, the XPOL 1 omnidirectional antenna, not suitable for a rural. It can be used in suburban, but not recommended. it really starts shining in an urban area, and very much so in a dense urban area. We've got those like the Madrid case study that we had where the towers were close by. The OMNI 600 can work in a rural environment, but it really starts shining in a suburban and urban environment. And in dense urban, it's not that it will not work, but it's but in a dense urban environment, you probably would like to have an antenna with an ease of installation. So those are the omnidirectional antennas that we suggest for your LTE 4G 5G signal. Let's look at the directional antennas below here. Those are the directional antennas that we've mentioned. The XPOL 2 can work in a rural environment, but that really also shines in this suburban and urban area. And again, it's not that it won't work in a dense urban area, but directionality is probably not what you want in a dense urban environment. And then we move on to LPDA 92, the log periodic array. As we saw, very good for rural. It will work very well in the suburban area. But when we start getting into the urban area, you don't really want that high gain directionality, and it's not really recommended for dense urban. Yes, Stephen.
Yes, I just wanted to mention this. There is no clear and fast rule, so this is just a bit of a cheat sheet. And in some cases, the LPDA may work perfectly in the dense urban area. So this is just when you are not sure and how to select antenna for the layman. But there are cases where I would actually deploy an XPOL 2 or an LPDA in a dense urban area. But if you're not sure which ones to use, then this would be a very good cheat sheet to use.
Thank you, Stephen. Right, on our website, you're going to you will find various cheat sheets, the antenna shortlist, the long version, the popular LTE frequencies, the LTE frequencies, that is the antenna choice. And I may just add that we are in the process of publishing a router versus antenna selection guide. That'll go live. Just watch this space for that to come live. And then very briefly, certainly not last but least, is that we are busy developing an antenna that has the ability to take the router in the back, and that will, like you saw with the long RF leads and the attenuation of long RF leads, that will shorten the RF leads to a few centimeters or a few inches inside the housing at the back of the antenna, making full use of the excellent capabilities of our OMNI and our directional antennas. Now that is it from my side, Ilana. Thank you, and over to you.